Welcome to my class. Today's agenda, we will review the midterm exam. Okay, we'll provide brief feedback on assignment 5, answers, and some plan for the rest of my course. Okay. Okay, so the first thing first, I like to play a game. Today, you are the prof, I'm the student. Okay, I'm going to show you how I work on the midterm exam. And I got too many questions. Like student asked me, how's it possible to finish everything in 2.5 hours? It is possible. All the exams that I design, right, is very fair. If you work more than the time that because when I write exams, I always specify some time and how much you wait. If you spend more than the assigned time, something's wrong. Maybe your planning's wrong, the approach is wrong. Anyways, I'll go through that today. Okay. Okay. When you get an exam, of course, you write down your name, you write down the student numbers. Okay. And we'll start working. Always do not panic. Everything is it's nothing strange. You've seen all that before. What is the first thing? What is the numerical procedure that we use to obtain solution? Of course, is FEA, the finite elements analysis. Right? To start this, all FEA start with a planning. The planning phase for FEAs is pre-processing. During the pre-processing, you subdivide the problem into elements and nodes. And then you have to assume a shape function. Okay, assemble elements to represent the entire problem, and then construct the global matrix. I mean, global stiffness matrix. Apply what? Apply the boundary conditions and loading. And B, C, and load. After pre-processing, then it comes to the solution stage. Solve a set of linear or nonlinear equations. Yeah. A lot of algebra equations. Such as, we always do that, displacement value, the displacement vector. Oops. Oh, what did I do? Oh my God, everything shifts. Displacement. And finally is the post-processing. Okay, what is the computer program that help us? The mighty answers. we can maximum, we work on 10 by 10 matrix, but answers can deal with a matrix as large as thousands by thousands, millions by millions. Okay, when we need to invent a new element, we use the minimum potential energy approach. Minimum total potential energy. Or the external force stored within material is called a strain energy. Okay, you get all this, you get 15 points. Okay, question 2. It's about 30 minutes. Okay, and then it's deal with string elements only. Okay, so the figure 1 is an example, and you just follow the same routine and work on all other figures. Okay, to see problem like that, I deal with I start with the stiffness matrix of the first portion between nodes 1 and nodes 2. Between nodes 1 and nodes 2, we have 2 elements, and each one is 1, 1, negative 1, negative 1, right? So 2 of them will be 2, negative 2, negative 2, and 2. So this part is done. And then there are 3 elements between nodes 2 and 3. So will be done. Okay, you know what? Right here, I didn't add it up. 2 plus 3, it is 5, right? But you know what? It's totally legit if you just give me an answer like this, 2 plus 3. And you know, it's even better because you show me how you work on it, right? So nodes 2 and 3 is done. And then between 3 and 4, there's only one element. So nice and clear. Stiffness matrix is done. Now we apply the boundary conditions. Nodes 1 is not doing anything. It's locked. Nodes 2, yeah, there will be a 10 pounds to the left, right? By the way, we rewrite down the applied force 10 pounds. So there will be a displacement. Node 3, yeah, there will be a displacement as well because there's a 10 pound to the right. Okay, remember, always give me the sign. Okay, negative. If it's to the left pound, to the left, it's 10 pound negative. And node 4 is tied totally. Okay, and then because node 1 is a 0, it's tied, so there is a reaction force acting on node 1. And because node 4 is a tied in 0 displacement, there is a reaction force on node 4 as well. So with this, you get perfect for this course, for this, no, not the course, for this figure 2. Okay, next one. Aha, this is tricky here. We have a special elements that tie between 1 and node 1 and node 3. Let's start with this, okay? So node 1 and 3, there's a special element. Let's deal with this first. This 1, negative 1, negative 1, 1. And then between node 1 and 2, there is a 1 element only. So this is a plus 1, negative 1. And we deal with there's a combo between 2 and 3. So which is a plus 2, negative 2, negative 2, plus 2. And finally, there is another combo, which is a +2, -2, -2, and 2. Okay, and then we deal with the displacement vector. Node 1 is locked. Okay, Node 2, it is locked as well, but it is locked with a displacement, which is a -5 inches. Okay, and Node 3, there is a positive force on it, so there will be some sort of displacement. And Node 4 is 0 as well. Okay, because on the right side the displacement is fixed, so there will be a force on F1, and there will be a force on F2 as well, and finally there will be a force on F4, Node 4. Okay, another one done. I need some feedback. How are you so far? You know, do you have any questions?
How come we have F2? Supposed to be 0, right?
F2 should not be 0 because there is a displacement on Node 2, which is a -5 inches. And if there's a -5 inches on Node 2, there must be a force. There must be a force making it -5 inch. Can you picture that? No, if always whenever there's a known values on the right, there must be unknown on the left. Vice versa, when there's a known values on the left, there must be a unknown value on the right.
Okay, yeah, sure.
No problems. Okay, figure 4. Wow, what a mess. No problem. You handle it like others. Okay. Between nodes 1 and 2, first element is a 1, -1, -1, and 1. And there's another element here, which is a broken spring. The broken spring doesn't give you any stiffness. So you know what? Forget it. Okay, between nodes 2 and 4, there's a special elements tied together. So 2 and 4 will be right here, +2, -2, 2. Okay, and between nodes 2 and 3, there's elements which is a +1, -1, -1, 1. Oops, something's not right. Yeah, I think I did okay. Yeah. Hang on. I made a mistake here. Why did I +2 here? This is 1 only. This between nodes 2 and 4, there's only 1. It's spring element, one spring element only. Okay, and then between nodes 3 and 4, yeah, this is the special one, stronger spring with oops, -2, -2 +2. Okay, this boundary conditions for the first node is tied, nothing's there. Node 2, yes, there is something, which is a -6 inch. And node 3, it is moving. Why? Because there's a positive force on it. And node 4 is -12 inch. Okay. F1, F2, F4. So question 2 is done. Any questions? And it is well under 30 minutes. Right, question 3, nothing different, nothing major. We've done that before. It is similar to quiz 3. Okay, we have a 3 spring element, and then there's a special force applied to it, which is not a constant force. It varies. It varies along the elements. So we need a shape function to deal with that. We need to do I have enough space here to write it? Yeah, I guess so. Okay, first step. I'm gonna write it here. The local stiffness matrix. Okay, part A, local stiffness matrix. The K is AE over L, which is 1 times 1000 divided by, well, this is a 30 inch in total, right? So each element is only 10 inch. The K will be 100. Okay, so the K local will be K. S is the last digit of your student numbers, and then determine the applied factor of each element. Okay, don't let the unknown scare you. So we do it one at a time. F1 is integral from 0 to 10. It is the force function, 3x times the shape function, 1 minus x over L. L right here it's 10, okay, 10 inch. Right here is x over L dx. Okay, we'll rewrite this equation. We multiply them together. The first one is a 3x minus 3x squared over 10, and then 3x squared over 10 dx. The integration for that thing will be 3x squared over 2 minus 3x cubed over 30. 30. 10 and 0. Did I do it right? Yes. Yeah, so far. Which is x squared is 100, 300, 150 minus 10 to the 1033 30. Okay, 1 and then 100. Okay, so the fourth vector will be 50 divided by 100. Okay, this is the same for all students. Okay, fourth vector 2 will be from 10 to 20, right? And then which is s plus 2, 1 minus, same thing, same shape function. S plus 2. The integration will be x squared minus x squared over 20. Yes, and then this x squared over 20. And we take the values from 20 to 10. Which is a negative, hold on, 20 minus 400, okay. 10 plus, negative plus, so 10 squared divided by 25. 20 divided by 20 is 20 minus 5 equal 2 plus s, negative 5, 15. Done. F2 is done. Now finally F3. F3 is so easy. It's a constant number. Okay. There's no integration required. Okay. Zero and then 10 plus s. Okay, let's put it all together. Oops, it's a bit tight. Okay, the first force factor is 10, 50, 100. Okay, and then the second one is wait, so we did that one. So that should be same for all students. And then minus 5 times 2 plus s. Right? And then 15 times 2 plus s. So this is done. Plus 0 and then 10 plus s. That's the apply force. And then the total, oh my.
Do we have a reaction force on node 1?
Not yet. I have to apply the boundary condition at the end.
Oh, okay.
Yeah, I see. Don't rush to it. Okay, and then the displacement vector, I assume I know nothing. Okay, and then when I look at the diagram, only node 1 is locked. Everything is free. Okay, so this is 0. And then because this is a node 1 is 0, and there's an applied force of 50. So there, because it's 0, there's a reaction force tied to it. And then U2, U3, and U4. And then depends on your student number, you sub in the S, and then you resolve the equations. I don't care how you do it. You may use Excel, inverse the matrix. You can do the equation reduction. Okay, but if you're up to here, you get 80%, 85% of the questions already. How you solve it? Seriously, it is I'm not too concerned on it. But if you want to get perfect, you carry on. Usually, that's what I recommend. Up to here, you jump, you go to the next equation, and next question, and work on the next question, because this is what I like to see from you. Okay, this step show me that you understand FEA and how you solve the equation. Seriously, it is a computer's work. Okay. Any questions so far? All right, let's move on. How am I doing in terms of time? I start at 9. Now it's only 9:30. See, I'm very generous. I give you 45 minutes just for this question. Okay, finally, question 4, which is a big one. It worth almost almost half of the exam, half of the midterm. It's a 45 points, and it's a 60 minutes. Okay, you see a problem like that, again, don't panic. The first step, you draw something. You simplify everything into elements and notes. Okay, so okay, right here, I did not specify the where you put the note, but seriously, it doesn't really matter. I set right here at note 1, note 2, and then 3. But let's say, oh, I don't like that. I want you give it notes 3, notes 2. It's totally fine. Or I'm crazy. I want in note 4 and 5. Note 1, 4, 5. It's totally okay as well, as long as you're consistent. It's not so convenient, but as long as you're consistent about it, it's fine. How you name it, I don't care. I'll trace it, but that's my choice. I like it notes 2 and 3. And then, well, since I named the note, I sometimes depends, I will carry on. I design the degrees of freedom as well. Note 1, it is a beam element. So it's allowed to move up and down. Okay, when it's moved up and down, I like to name it a V1. Displacement along the x-axis, u. Displacement along the y, v. And it's able to turn as well. And for nodes 2, yeah, it's allowed to, it's same as nodes 1. It's go up and down, so it's a v2, and it's allowed to turn, so a phi 2. Now let's take a look at the other element, which is a truss element. Truss elements allowed to move up and down, and left and right as well. Oops, I missed something. This is a truss element. Nodes 2 is allowed to move left and right as well. So nice and clear, we know there are 2 elements, 3 nodes, and total, it has 7 degrees of freedom. So we will be dealing with a 7 by 7 matrix. Okay, first step, determine the local matrix for beam and truss element. I just pick up the formula sheets that I provide you, so you don't have to flip through your notes. Oh, by the way, I will provide a formula sheet for your final exam as well.
Sir, should we expect some multiple choice questions on the final exam?
I haven't designed it yet. Why? Do you like multiple choice? I can get some.
I thought they were all right. The one you did for the first test,
First test.
definitions.
Let me think about it, though. Because the first that midterm exams, right? I have some multiple choice on the Word document, and then I asked you to do a lot of writings on the question 3 and 4, and too many students have problem merging the Word document with the handwritings, the PDF. I might not do that in final exams, so I will see. Yeah.
Professor, so in this question, if there was a pin joint at node 2, will the degrees of freedom at node 2 still be the same?
I still have to specify it, because the elements allowed to move elements, the truss elements allowed to move u. Okay, but at the end, when I apply the boundary conditions, I set u to 0. Okay, but you do not worry about this during your planning stage. Okay, the pre-processing. During the pre-processing, during the plan, when you plan the final elements, you don't worry about boundary conditions for now. It just confuse you. My mind is so simple. I deal with I design what elements I use, what notes I use for now. We'll worry about U2 0 or not later. Okay, the first things first. Beam elements is E. It's not E A over L. It's E I over L cube. So which is a 1. What is it? 1E4, 1E3, and then 50. 4, 1E3, and then 50. Oops. Okay, so the K for the beam, lots of plug and play. Okay, I think the first term is 12, and then the second term is I forgot what is it. Okay. You know what? I just thought of a good idea. Okay, I am doing this by hand, but since you learn how to deal with a matrix with an Excel spreadsheet in the 2D elements, you may set up a good Excel spreadsheet to help you to create stiffness matrix. You just plug in the numbers in the Excel spreadsheet, and then it gives you a local matrix, and then you just copy the numbers from Excel and put it here. That'll work. Yeah. Anyways, this is the beam elements stiffness matrix. Oops, I forgot. I have to deal with the truss elements as well. Okay, for the truss elements, I need a information table. So this element, truss elements, is going from node 2 to 3, and the local K is EA over L, which is 6 times 1e4 divided by 60. 1000. Okay. The angle is, now this is tricky part. Okay. I am going from node 2 to 3. What angle is it? This is 90. This is 180 degrees. So from node 2 to 3 is 210. Do you agree? Or we don't even talk about angle at all. I just want to look at the cosine. Cosine is the adjacent side over the hypotenuse, this thing. So this side, the absolute value is a √3. This is 2 and 1, right? So we are moving from node 2 to 3, so which is a negative √3 divided by 2. And sine is node 2 going from node 3. So the we have to travel down by 1 divided by 2. So that's, if that's the case, so c squared equal to 3 over 4, and s squared equal to 1 over 4. And C and S is negative root 3 times -1, which is a positive. Sometimes I like to write it in a fraction, but right here I'm going to add them together. So I use a decimal point this time. Root 3 divided by 4 is 0.43.
What happens if you travel from 3 to 2?
Let's do that. Yeah. Note 1. Okay, you want note 2 here, right? And 3, right?
No, 3 to 2, like the way you show first. I mean, if you go to the first diagram, it's from 3 to 2. Yeah.
If I travel from 3 to 2,
Yeah.
that is a positive 30 degrees. So same here, you know, I like to travel from, because, okay, when you set up the, when you
Yeah.
set this, the matrix, right, it has to go from nodes 2 to 3. So if you want to travel from nodes 2 to 3, in this case, I have to reverse the node elements. You know what I'm saying? I have to reverse the name of the node. So basically, what you're saying from node, okay, in my case, you want to travel from nodes 3 to 2, okay, which is not right when you build your trust elements. I wouldn't say it's not right, but it just screw up everything. Okay, but basically what you mean, I know what you mean. Basically, you want to travel from this node to that node, right?
Yeah.
Okay, so let's do that. So in your case, basically you want to name these nodes 2. Okay, now by the way, this is unrelated to what I'm doing right now, but I will set it up. Okay, 2 to 3, and then the k values, okay, theta will be 2 to 3 will be 0, 90, and then because this is 60, so 0 to 2, 2 to 3 will be 30. However, I do not like to deal with an angle at all. I always look at the components of the trigonometry. So cosine will be this edge over 2, positive. Sine equal to 1 over 2, because this note 2 to 3. This is 1. Okay, so in this case, cos square will be 3 over 4. S will be 1 over 4. S equal to 1 over 4. CS will be 3 over 4. That's going from traveling from nodes 2 to 3. Okay. Different nodes naming. Okay, so the local matrix for the trust element is done. So part A is complete. Any questions so far? Okay, moving on. Part B of the questions. Calculate force caused by pressure load. Again, this is straight from the equations. What was the equation again? I believe it's a work load, pressure load times length over 2, and then something like that. Okay. I did that previously. Remember, it is a 20 pound per inch down. So workload is -20. Okay. If there's something pressure going up, it's positive. So B is done. Now that's the exciting part, construct the global matrix force vector and apply BC. When you work on the global matrix, the first step, you label your local matrix, and then according to the new address, you move that numbers into the new space. So I named this is a V252, V151, V252. Okay, for my truss elements, I have a U2, V2, U2, V, sorry, U3. You know what? So much better. Okay. Part C. Okay. So we have 7 degrees of freedom. What I like to do, I always write down the displacement vector first. So according to this, I can adjust where I want to put the each values within the global stiffness matrix. We have V1, angle 1, V2, phi 2. And then what else? We have U2. I have V2 as well, but I already have it up there, so I'm not going to write it. So it will be U3 and V3. Any questions so far? Okay, pretty good. Okay, to help me to allocate each values within the matrix, I write it one more time. Okay, so oops. Now we just move them. Okay, the first value hasn't changed. There's no add or subtract. So it's 80 times 12, 960. And then right here, 80 times 300. 24,000. And then this, you know what? If you look at the beam elements stiffness matrix closely, you just have to evaluate a couple of them. And then the rest of it is the same. You just copy the numbers over again. Okay, right here is 12. This is negative 12. So you just negative of the value. And then right here is a 24,000. This will be the same. So will be negative 960. Hey guys, sorry man, I lost you for a bit. You guys hear me good? Sound check.
Yeah, we hear you.
Okay, perfect. You know, you didn't miss much. You know, I'm just still working on that giant matrix. Okay, you know what? I'm not going to copy all values, but I'll show you the key ones, you know, that I need to add together. I think it's a V2
Sir,
by A2. Yes, what's up?
we can't see your screen, or at least I can't see your screen.
Yeah, I can't see it either.
Okay, how about now?
Yeah, now we can.
Okay, I'm not going to show you the how I copy all the values. It will be so boring. Okay, you just do it carefully, but I want to show you which value is affected. It's too tight right here. Right here, the V2 by V2. This is 960 plus 1,000 plus 250. 960 plus 250 for V2. Okay. And then the rest of it is the same. Yep, only this one is affected. Okay, I assume you know this one. Okay, basically you just move all those numbers into the new box. Okay, patiently, you know, be careful with them. And I can tell you only this one is affected, this box. All right, let's deal with the force factor. The force factor right here. Let's deal with the first part of it. Okay, that's the applied force from the uniform pressure. Okay, and then what else is there? 1000s on node 2 down. On node 2 down, so it is negative 1000s. And then there is a hold on. Let's apply the boundary conditions. This is 0, 0. And then V2 is allowed to go down. Psi2, yes, allowed to turn as well. U2 is locked in place. The truss element's not moving to the right. And then this is 0, 0. Okay, because there is zeros on those values, so F2x, there's a reaction force on 3x and F3y. And there's a reaction force to hold that in place. So it's a plus F1 plus 1. Okay, if you can show me this, of course, with all the numbers on it, okay, you get 80% easily for this. Ready? Okay, now, any questions so far on this? And I need you to solve for V2. And because, you know, it's as V2 is different for each student, depends on your student number. Okay, for, where are we now? Let's see. Deflection done. And then the axial stress along the truss. Back into the equations. Force axial. Which is the T okay, so what you do is you solve for 2x, F2, F2x, F2y, F3x, F3y. Get them from the equations. You plug in numbers here. And then you construct T minus 1. T minus 1, I believe, is flip back to note again. It's very similar to example, truss example, the part 2 of the truss example. Yes, right. Okay, and then stress will be force over area. Okay, if the beam sinks too much, please suggest 2 ways to improve the design. Many ways to improve it. You know, we have a thicker beam and truss. more trust. Material with a stronger E. Okay. There are many other ways to do it. There are some unacceptable answers, like reduce the load. Okay, let's say, well, in theory, it is acceptable. Yeah, if you reduce the load, deflections is less, but you are changing the design requirement. And also, there's another one that I cannot accept, that is a shorter beam. Again, you are against the design requirement. The bridge, the length of the bridge is fixed. Okay, we don't want to change that. Okay, part G, that one is exciting. Okay, for part G, I don't want you to solve for it, but I want you to replan the FEA. Okay. How do I do with that if there's an extra load acting on the middle of it? So again, do not panic. Repeat just what I did. First step, name the node. Because I have an extra load on it, okay, I must have a load right there. Because the node, right, it is able to receive information and tells you some result. No node, we cannot do anything. Did you work on a ANSYS lab 2? Okay. When the element's too coarse, you cannot detect very good stress values. So that's why locally you put more nodes around the effect area to get more information from it. Okay, and then I name the nodes, and then I name the degrees of freedom. 2, 5, 2, V3, 5, 3, and also this belongs to the trust element as well. All right, so it's a U3. Finally, U4 and V4. So we have a 9 by 9 matrix. Okay, and then there's a crazy K. There's two beam, and one truss. Okay, that's your FEA plan. You just show me a diagram and how you name the degrees of freedom. Now, let's put them together. V2, 5, 2, V3, 5, 3, and then we have U3, V3, U4, V4. Wow, so big. Oh, but I forgot, there's a local apply force, right? So instead of a force, it is a negative. What was it before? This is negative 500, right? Now the length is divided by 2, so everything divided by, so this is divided by 2, and this is by 4, okay? 50 minus 104167 minus 250, and this is plus 104167. Okay, so the second element, oops, see, I made a mistake. You should add it to get right there. Okay, the first note is a 2000 S, and then the new applied force at the center of it, right? So actually that is the new applied force, new note. Okay, hold on. Let's see. This is 0, 0, and then the U 0, 0, 0. U, that's a U. Sorry, guys, that's a U. Okay, F3, F4X, and then F4Y. That's it. Apply the rounding condition, then do not solve it. Right here. That's the end. Any questions? Okay, your final exam will be a similar format. I'm writing it now, and based on your feedback from all the quizzes and the midterm, I will design a fair final exam for you guys. Okay, nothing strange. And as usual, I will provide a formula sheet for you. You use it during the final exam, and also you may use it as a study guide. Basically, the formula sheet will tells you what equations you're going to use. So you focus on those areas for your final exam.
How many questions?
I haven't finished it yet. I haven't finished it.
Okay, can I ask you one more question?
What is it? Tell me, yeah.
Like for the question 3, when you analyze the truss, right?
Question 3.
Sorry, 4. Sorry.
Oh, yeah. Okay. Yeah. Yeah.
So like I went from node 2 to 3.
Okay.
And I put the angle as 30 degree, and you highlighted this as maybe incorrect.
Where do you go from 30 degrees?
From like
from
where,
node 2 to 3.
Like from like I would like number this as 1, 2, 3.
Yeah.
Right. So I went from 3 to 2. But like it would be the same as you did, because like you number this as 1, 3, and 2, right? So should give the same results.
It should, yeah. It should.
Yeah, but like I don't know why you highlighted this as maybe incorrect, or like I did something wrong.
I won't deduct any mark on this, you know. But I'm just saying that from node 3 to 2 is not the right thing to not the right thing to do to construct your local matrix. Yeah.
But
I highlighted it. I might have questions because when I see that, I don't feel comfortable. Okay, but I won't deduct anything.
Oh, okay. So
yeah.
Okay, I thought like you reduce some marks.
No.
On that one.
Okay, it's not the right thing to do. right? You usually go from node 2 to 3. You know, you don't go from node 3 to 2. Why? Right? But you know what?
Oh, because like it will be easier to just like figure out the angle, right? It's 30 instead of 210 as you did
Okay,
in the first one.
why I say that, because if you have node 3 going from node 3 to 2, right? Those numbers will be interchange.
I think I got them the same. Let me check.
Anyways, okay, I don't think I deduct anything, but in the future, move from nodes 2 and 3 and then start from there. It's, you know what, seriously, you will feel so much better when you move from. Anyways, small issues, okay? Right? Okay, let's move on. Okay, today I finished that. I reviewed the midterm exam with you guys. Brief feedback on assignment 5 on a 2D element. Okay. I have marked your assignment 5. You guys did very well. I'll show you how I construct my
Professor, would you be posting these notes that we went over today?
yeah, I can do that. Yeah,
Okay, thank you.
you're welcome. Okay, I will have to remind us. Send note. Turn. Okay. Okay, I have marked your assignment 5 2D elements. Okay, and I asked you to do I work on the Excel spreadsheet for the 2D elements. Most of you did. There are few students, they do everything in hand calculations. Kudos to you. You guys are my hero. You know, when I do the 2D elements, stiffness matrix, by hands, I always out of patience. Okay. Anyways, this is a okay, there will be, for sure, I can tell you now, for sure, there will be one question on 2D elements in your final exam. Okay, it's your choice. You may hand count everything, but I strongly recommend you do with an Excel spreadsheet. Quiz 5 is okay because you only have one element, right? So hand calculation is not too bad. You know, what if you have two 2D elements? What if a 2D element is linked with something else? Trust elements, and then you need to save time. In order to do so, you need a strong Excel spreadsheet to help you to achieve that. So now I'm going to show you how I did my. Well, most of you did it already. This is how I construct my 2D element matrix. Okay, the first quadrant, it is for your input. You input, okay, all the blue stuff is input. Right here, it's a free coordinate system, free coordinates for the node. And in my case, I think I defined that in a question already. You know, 0, 30 is node 1, 0, 0 is node 2, and 30, 0 is node 3. And then there's another input column for the elasticity, thickness, and Poisson ratio, 0.3. Okay, from those information, from the coordinates, you calculate alpha, beta, and delta. How is it done? Well, it's straight from the equations in your note, you know. Okay, which is a B3. Well, in your case, it will be something else, okay? But in my case, it's B3 times C4. So it's a X2 minus Y 3, sorry, x2 times y3. And then b4, which is a x3 times c3. See how confusing it is? That's why having a Excel spreadsheet will help you. Okay. Right here is two areas. Okay, in this case, the area is positive. Sometimes depends on how you name the coordinates. The 2a can be negative. It could be negative. But when you do the constant, okay, t times a, you pick the absolute value for area. But when you do the shape function or something, sometimes you have negative 2a. Okay, and then you calculate a constant for E for the electricity, elastic matrix. So it's a 3 by 6 times 3 by 3 times 6 by 3. You multiply string displacement matrix T transpose times E right here, and then you assemble the 6 by 6. Done. And then that's it. Because of the boundary conditions, right? I'm down to, from 6 by 6 matrix, I'm down to one equations only. So right here, we calculate V1 is not even 1/1000 of a deflection. So again, if you have a matrix, if you have an Excel spreadsheet to help you to write 2 by 2, 2D elements, it's good. If not, please work on an Excel spreadsheet as soon as possible. Okay.
Sir, I have a question.
On what? On the 2D elements? What?
Yeah. What happens if we have another node? Like,
Yeah.
how would you calculate for, like, let's say, 1 second, the beta and alpha? Because like if you are calculating for like alpha 1, you always consider like node 2 and 3, right?
Okay. 2D elements that I show you in this class, right, only have 3 nodes. Node 1, okay, depends how you name it. I like it node 1, 2, and 3. If you have one more node, let's say, okay, I have extra loading right here. I need one more node, node 4. Then you split that into a 2D triangle. And then from there, you have a elements 1 with a node 1, 3, 4. And then elements 2, you have node 1, 2, and 4. Okay, and each element you have a 6 by 6 matrix. Very good questions, by the way. Okay, let's deal with them.
So, sir, we
Yeah.
cannot do them together, right?
No, because your Excel spreadsheet is designed to
For
take
only 3, right?
only 3 nodes. Yes.
Okay, I thought like there is another way like to just combine them.
No,
together.
no, you combine them with a 2D elements.
With 2 matrix, yeah.
Okay, yeah,
sure.
that's right. And then you know what? Let's carry on. Let's move them. It's a U1 V1. Oh no, U1 V1, and then U3 V3, and then U4 V4. Right, and then right here is a U1 V1, U2 V2, and then will be U4V4. And then you have two small matrix, you go and build a big one. And depends how you lock it. Maybe you lock like this, and then, oh, by the way, if I do a node like this with a force vector like this, you're gonna hate me because you know what? There's a lot of trigonometry going on. You know what? I'm being nice. Okay. X. No, let's call it a 100, and then this is a 1000. Okay. So I locked nodes 1 and 3. Nodes 1 and 3. So this is 0, 0, 0, 0. And then nodes 4 y directions is a plus 1000. Nodes 4 y direction is plus 1000. And nodes 2 y direction is a minus 100. Okay, and the rest of it is okay. The F1x, F1y, and then U2 is 0. Okay, there's no force acting on it, right? U3 and U3 V3 will be some reaction force. And U4 is 0, but I have a positive force on it. So that's it. And then you solve for it. If I have a question like this, you up to here, you get 80% already. Okay, and see right here, that's why, you know, hand calculation is painful, you know, so you need an Excel spreadsheet to help you to construct the local matrix. Once you have the Excel spreadsheet to give you like a 630, this is a 6 by 6, 36 numbers, right? And then you just, I don't care, maybe you can, okay, let's go back to the, okay, once you have the stiffness matrix, you may copy it and paste it in your, can I paste it here though? I never tried. Can I paste them? Yeah, that's right. Perfect. So this is element 1, and then you have another element 2. Okay, and then you add them together, becomes an 8 by 8 matrix. Handwriting, paste, copy and paste, doesn't matter, as long as I understand your presentation and you write something about your work. And so you let me understand your approach, I give you credit for it. Okay. Okay, what else I owe you today? You know, review midterm exam done, brief feedback on the assignment 5 done, and one more note on 2D elements. Good. Okay. Now let's do some work on answers. I mark your lab number 1. I'm very impressed. good job so far. And some feedback for student not doing so well. Okay, and also like to share with you what is my marking scheme, what do I look at when I read your report? Okay. Okay, you refer to the ANSYS report requirements. I have that uploaded in Avenue to Learn, the report guidance, what is required in the report. You follow that. Most of you did. Some additional remarks when I mark your ANSYS lab, you usually, most of you did it, but you miss out, you mention, okay, this finite elements analysis is being conducted by ANSYS version whatever. It's a student version. Then you can cover yourself. Okay, I have a few students, they are not able to construct the S table, and then the von Mises stress is not available, whatever. Okay, sorry, I cannot help you on that. It must be some student versions setup issues. You just write about it, because when we have that class in person, all the ANSYS version we have in my master university, they're perfect. We don't have issues like that. But due to distant learning, you have to download it, download the student version. There might be some setup issues. So if you mention that in the report, okay, because of the pandemic, we are downloading the student version, there must be some setup issues. I can get you the displacement, the deflection. However, there's some ability is missing. I don't know why. Seriously, I cannot help you on that. Some students did it, some don't. Maybe you can talk about it. But as long as you mention that in the report, then as a customer, okay, I understand now. Okay, because of this, you're not able to deliver all the requirement. But the major ones is there: the deflection plot, how deform the displacement. Yeah, it's all good.
You understand, but will you pay full price still?
Somehow in this case, I will ask for a discount. Yes. Okay. But you know what? In this case, right here in the final elements, you are the customer, not me. You paid my school, and I deliver what I know. But those students, those are student versions setup issues. Sorry, man, I cannot help you on that. Okay. But I'm very generous on marking. Okay. Okay. Second feedback. Not too many people. Oh, I would say half of you guys did it. But not too many people mentioned the elements type that you use. Well, in like all the theory stuff, we select the type of elements that you use to resolve your problem, right? When you see a beam, you select the beam elements matrix. When you see a truss, you use the truss matrix C square, S square. Okay. Same here. When you work on ANSYS, you write about which elements you use to to model your problem. So you just talk about it, okay, that we use the beam 188 element designed by ANSYS to simulate your problem. And when you see a truss, you use link 180 to simulate your work. Okay, then the boundary condition descriptions. I don't like that when you say I logged node 3. What is node 3 to you? What is node 3 to me? Can means different thing. The best way to do it is draw diagrams, and then you just mark it up. Okay, I log this node, and then talk about it, which is the corner of the structure left-hand most corner of the structure, and then I lock all degrees of freedom, or I let it slide on the x-axis. It's a rolling joint, fixed joint, pin joint, or I lock the moment as well, you know. Okay, talk about your note. Okay, another issues, okay, most of it, a few reports, they have like 10, 15 pages of screenshots of the figures, screenshot of your notes displacement. Yeah, I have displacement of all notes, you know. Well, it's not necessary, because if you have too many pages of things like that, I miss out all the crucial things you want to tell me. In this case, like, more pages of big report doesn't mean a better report. Just a few pages, talk about a few pictures, few pages of wordings with pictures, tell me all the crucial key points, then it's good enough. Okay, you don't have to show me all the screenshots, how you build your elements. Anyways, the right amount of information is the correct information. Okay, and when you provide a unit, provide the numbers, please tell me a unit of it. Okay, my deflection is 2 what? You know, 2 inches, meters, feet. Okay, and finally, if you present pictures in your report, try to write something about it. You know, figure 1 is a deflection of the structure. Figure 2 is a stress plot of the structure. Okay, if you have all this, you know, with the report requirement that I specify in Finite Avenue to Learn, you get up to 80%. And then the rest of it is the overall presentation, how you write. Do I feel comfortable when I read it? Does it look like a professional report? I read FEA reports for so many years now, from work, from students, from customers, from clients. Yeah. So if you have this information, you get 80%. You know? And if you write an amazing report, you get 90, and then go, and then so on and so forth. You know. Any questions on FEA? On ANSYS?
Uh,
Good luck to
Chris,
your, yes, what's up?
I have a question, but not regarding the report, about the ANSYS. You know how we get the plot according to the displacement and stuff? Can you show us how to get back to the normal? Like, I mean, how to get that thing off?
I
Like,
do not know what you mean.
uh, let's just say on the lab 1, when we did the displacement of the displacement vector and plot the graph, how do we get it back when we had the normal distribution, like without any deflection?
Oh, I think I know what you mean, but I cannot show you here. It is, you play around with the plot control. You plot under the tab plot control, you just replot everything. Man, that's why I hate distant learning so bad. Okay. Under the plot control tab, there are many things. You can plot the elements only, notes only. Okay, and then you can go back to the original how you set up the model.
So I tried to mess around with it and then I just lose my whole thing. Like there was nothing on my display at all.
Any comments from other students? You know, help him out. Anyways, that's only comments I can give you, like only feedback I can give you. Play around with the plot control and then don't be
What
scared.
was the question?
He was saying that he plotted deflection plot, and then he wants to go back to the illustration without the deflection. Is that right? Did I catch your question right?
Yes, yes.
I think you just play around with plot control. And under plot control, you have many things, just try on each one, don't be scared.
Or like the deformation shape or the deform shape.
Yeah, that's right.
Yeah, I think he can go back. Like if he wants to show the deform shape, and then if he wants to show the nodal solution, that's fine.
Yep. Anyways, that's the only comments I can give you. Just play around with it. More practice you have, you better you get. And then in your case, I trust me, it has to be something to do with the plot control. Try out even different tab, and yeah, play around with it. And then, wow, the worst case, you do this assignment over again. Those are simple elements, right? By the way, I tell you something. When we were working in Pratt & Whitney, Canada, when we designed the aircraft engines, we spent like weeks and weeks to build on the model. Okay, and then if we make any mistake, there's no undo button, right? So we save different versions of the model. So let's say we screw up something and we will go back to what we had yesterday. We just retrieve the file I saved yesterday to get back to where it was. Okay, instead of starting over from zero, from scratch.
Professor,
Yes.
I have a question. For the labs, the feedback that I got was very general. I would like to know if you could give us like more detail, like feedback, so we know exactly where we lost marks and how many marks were deducted from each things that we missed.
I just did, I provide general feedback because I cannot provide detailed feedbacks for everyone. So that's why I have conduct today's lecture, on additional remarks and things that I like to see right here, answers version, element type, bad examples on how you log the note, too many screenshots. Yeah. Okay, how about this? There are 5 labs. You are allowed to drop 1, maybe 2, depends on your progress. Okay. In the future, when I mark your labs, I can provide more details. Okay. Okay. But all the details, all the things, all the feedbacks I want to provide you is happening today. Yeah. I just did.
Okay.
Those are the general descriptions. Yeah. Okay, I am on task 3, brief feedback on lab 1, more guidance on future lab. I just did that. Remind me to talk about answers error, software error. I did that, okay, there's some error I cannot help you with. It must be student version setup issues. Okay, lab 5. There are 2 portions of it. The first portion has videos. The second one doesn't have a video, because I assume you must know answers pretty good by now. Okay, and also lab 5, second question has a lot of freedom on it. How you design that bridge, is totally up to you. But as long as you describe the problem, same here. What elements? What is your model? What are you trying to simulate? What elements you use? Okay, and describe your boundary conditions. What's your loading? How you define your loading? How many cars, trucks you're running on it, right? and how you lock the bridge. I think it's a bridge, right? Yeah. Okay, and one more thing, there will be a ANSYS final report, which costs about 20%. Yeah, I have a rough idea how I'm gonna test you, okay? And I'm just gonna write this down. This is very similar to your labs, but just a bigger report, bigger problem, more notes maybe. And stay tuned, you know, I might give you a choice, on how you work on this, because some students is very, very good at answers, but not so good at reports. Some students love to write, but not so much patience with the answers. Anyways, I'm working on it. Stay tuned. Okay, by the way, the final project for this answers report, I would say it would take you a few hours to work on it, but for sure, I'll give you a lot of many days to prepare that. And because it's an assignment, MASF doesn't apply. Okay, don't. Okay. There's some changes to the mark distribution. The ANSYS lab, I will take best 4 or 5 for now. Depends on the progress. I might take less, but for now, I like to okay, because some of you do not have time to finish all labs, and then once you finish 4, you're confident you're good enough, then you can drop out lab 5, because I'll just take the best 4 or 5. Same as the quiz, I'll take the best 4 because I still see some student missing the quiz or assignment number 1 and 2. It's okay, do not submit that. I close it already. I'll take the best 4 of 6 that we have. Okay, what's the plan for the rest of the course? Okay, today is July 3rd. I reviewed a midterm for you, and you have a good start with answers, and you just carry on, move along. Okay, finish all the labs and finish another project, big answers project before the end of the term. Okay, for next week, we're gonna have a lecture on the modal analysis and thermal analysis. Okay, if you're not too busy, please join us. Okay, because vibration and a thermal is our biggest enemies for the structure. Okay, thermal fights, vibration. July 17, I want to assign that as a study week. So if you have any issues, any problems with answers, midterms, anything related to this course, let me know. We'll work on it together, and I'll help you to study your final exam. July 24th, I want to, let's fix it. July 24th is our final exam day. Please make yourself available. So as usual, the night before, please sleep well. And also no panic, no stress. My job is teach you FEA. It's not my intention to fail everyone, okay? Seriously, I feel bad when I fail someone, okay? Because I want you to learn something and I want you to do well. So if you have any questions, prepare everything by July 17. We'll go through them together. And then that's it. We won't have any more meetings. There will be an ANSYS final project due on July 30th. And then that is the completion of the course. Any questions regarding the plan?
Sorry.
No, don't be sorry.
If the final exam is July 24th, is this the final exam for ANSYS?
No, no. Good one. Final exam for July 24th is only for theory. Only for the written exam. Only all the stuff that it's like your midterm, you know. It's like your midterm plus 2D elements, modal analysis, and thermal expansion. Absolutely. July 24th, no, July 24th exam does not include answers. Answers, you're supposed to work on a final report, final exam project. I haven't finished this. Anyways, I haven't finished both the final exam, and then the answers report. But you have plenty of time to work on those things.
And when will be the ANSYS midterm?
July 30th.
Okay, so it's one thing only.
Yeah, that's right. It's one thing. Actually, it's not really an ANSYS midterm. It's ANSYS final assignment. Okay, which is a bigger. But let's consider that as a bigger lab. You know. Questions? Any questions on the plan? Well, if you don't have, okay, what is it?
For the final, is it gonna focus more on the 2D elements and modal analysis and thermal analysis, or is it gonna be cumulative?
Could be anything.
Okay.
But I promise you, nothing strange. You know, you've seen all those before. Nothing strange, but not identical though, you know?
All right, makes sense. Thank you.
Okay.
Great.
Okay. Yes, what's up?
Can you allow us to resubmit the lab 2 with all those remarks so that we can get better marks on it?
You submit it anyhow, you know? Or yeah, you submit it, yeah. Did I close it? The mailbox still open.
Okay, so we can resubmit it and then get better marks at it, right?
Yeah,
Okay,
sure.
thank you.
How much time do we have to work on the final project, the ANSYS final project?
I would say up to three hours, you know, because that's what I did in a in-person lecture, you know. I logged every student. Sorry, I shouldn't say logged. I let student come into my class and finish the project within 3 hours.
Okay. Then it's supposed to be 31st, right? It's not 30. 1 second.
What, you want it 30th, 31st? I can do that. Yeah, because I want you to have a nice break in the weekend.
Oh, is it like during the lecture hours or
No, it's not.
outside?
Okay, when I was doing the in-person lecture, yeah, I let students finish that in class because we have amazing computer and amazing answer software in that lab. Right? So but now it's an in-person, sorry, it's an online class, right? So I let you finish that anytime you want.
In 3 hours, right? We have 3 hours, you said.
Okay. Like, again, I was saying I suggest time is 3 hours, but you have your assignment and work on it. Okay, you know what? I'll post the I'll finish up and I'll post the final project by a week. You know, okay, you have plenty of time. You have more than 3 hours to work on it. But what I'm saying is my suggest time to work on this report is about 3 hours, 4 hours. Yeah.
Okay.
Sure, I think there's a confusion because people are thinking that it's going to be like an exam.
No, it's not. No, don't worry.
In front of the computer doing it.
No, it's not. Okay. The exam, yes, I will post the questions like 9 a.m. in the morning, and you work on it. You hand it in by noon. But answers report, no, it's not. I will post that probably later, mid July, and then I ask you to hand it in by the end of July. Okay.
Oh, okay. So there is no like specific time, right?
It's like a bigger lab. Yes,
Oh.
consider it as a bigger lab. Yeah.
But like I can spend more than 3 hours, like 5, 6 hours. That's fine, right?
I don't recommend it, but up to you. Go ahead. I want you to enjoy life, you know. Not like me, I'm stuck with answers. I'm stuck with FEA all my life.
Okay.
Yeah. Okay. Final task. If you're not tired of me, let's do some lecture on modal analysis. I don't recommend it now because I think you're tired of me. You know, we have enough information for today. Let's focus on the modal analysis and thermal analysis next week. And prepare more questions for me. And we will work on that. Okay, what do you say? So far, let's do recap. What else do you owe me? You owe me all your labs, no, but I'll pick the best 4 or 5. You owe me a big major report on ANSYS. Okay. And in terms of a theory lesson, you owe me 1 more assignment, which is assignment 6. And then there will be a final exam on July 24th.
Sir, when is the major report due for ANSYS?
July 30th. Okay. Tentatively.
Oh, I see that.
July 30th. Tentatively. But it's supposed to be fine-tune it. Yeah, I'll fine-tune it a bit. So any more questions for today? Long lecture today, no breaks. You know, thank you for your participation. So I will see you next week. Good luck to your answers. Good luck to your anything. Okay. And good luck to the Montreal Canadiens as well. You know, they are in deep trouble.
Chris, somebody's
gonna get
asking
swept.
question in chat.
Say it again. What do you say? They're gonna get what?
Somebody's asking a question few times for the lab 2, question 1. Do we need to hand calculate the normal stresses?
Let me see. Oh, by the way, if you don't have questions on these issues, you may hang up and have some fun this weekend. Okay, let me see. Yeah, that's right. I missed that. There are few questions on with table not being able quick fixes. So after solving, select a report and set last. Okay. Take this as a good feedback and try it on yourself. Yeah. Make sure you save often so you can go back to your previous work. Yeah, that's what I did, you know. Thanks for the feedback, guys. Yeah, okay. A lot of my issues were solved by Lab 2, question 1, do we have to hand count? Yes, please. Yeah. You hand count and then you compare that with your ANSYS calculated stress. Yeah, and then well, the hand count, the stress is not too difficult. Okay, just the net force divided by the area, cross-sectional area. Okay, any more questions?
Thank you.
Okay. Like, good job. No, oh, by the way, who